Hey everyone, Mr. Hauk here. In today's video, we're going to be proving the law of sines and using the law of sines to solve oblique triangles. Let's go ahead and get started. So, what is an oblique triangle? Well, we know from earlier in the course, we spent a lot of time learning how to solve right triangles. Unfortunately, not every triangle is going to be a right triangle. An oblique triangle is any triangle that is not a right triangle, meaning it's any triangle that does not have a right angle. This means that oblique triangles can be acute triangles, meaning all three angles of the triangle are less than 90 degrees, or an oblique triangle could be an obtuse triangle where one of the angles of the triangle is greater than 90 degrees. Unfortunately, with oblique triangles, the trigonometry that we've learned previously in the course is not going to be enough to solve them. We're going to need a more powerful tool. So, before we learn about that more powerful tool, let's talk about the convention for labeling parts of triangles. If we look at this figure right here, notice that the angles are going to be represented with capital letters, usually A, B, and C, but it doesn't have to be A, B, and C. And the sides are going to be represented with lowercase letters. Also notice that the sides are opposite of their corresponding angle. Okay, so that's how we're going to be naming these triangles. And what we want to do in this unit is we want to be able to solve these oblique triangles. And what we mean by that, what we mean by wanting to solve a triangle, is it means that we want to find all the measures of the three sides and the three angles. So if we can find all angle measures and all side measures, that means we have solved the triangle. Okay? So, however, like we mentioned earlier, we need a more powerful tool because our right triangle trigonometry is not going to work for these kinds of triangles. We're going to need something called the law of sines and the law of cosines. And we're going to spend this lesson looking at the law of sines. So, how do we establish the law of sines? What is the law of sines? Well, to figure it out, let's consider an oblique triangle. And what we're going to do is we're going to take an altitude and we're going to drop it from one of the angles. Now, we're just going to go ahead and pick angle B here. So we're going to drop an altitude, and this altitude is going to be perpendicular, in this case, to side AC. And notice that since it's perpendicular, by dropping this altitude, we actually get two right triangles. One right here, and one right here. Now, since we have now created two right triangles inside of this triangle, we can actually use some right triangle trigonometry. We can use sine, cosine, tangent if we needed to. So the law of sines, here's how we can go ahead and establish it. So let's look at this first right triangle right here, the one that I have kind of highlighted in this laser pointer. Well, if I look at angle A, if I took the sine of angle A, it would be equal to, well, we know sine is opposite over hypotenuse. So again, we're looking at this triangle right here. Well, opposite of angle A is h, and h is what we called the altitude that we dropped. So we know that sine is opposite over hypotenuse, h is the opposite. In this triangle, c is the hypotenuse. So sine of angle A would be h divided by c. Now let's look at the other triangle, the other right triangle right here. Well, this time, if I look at angle C, if I took the sine of angle C, so the sine of angle C, again, it would be opposite over hypotenuse. Well, in this little triangle right here, the opposite leg is h, the hypotenuse would be a. So sine of angle C is equal to h over a. Now notice that for both of these equations that we just set up, they both have this h right here. So maybe if I can isolate the h in both of these equations, I can go ahead and use substitution to set them equal to each other. So let's do that. Here, sine of angle A equals h over c. Let's multiply both sides by c to isolate the h, and we get that c times the sine of angle A equals h. Doing something similar here, let's multiply both sides by a, and we're going to get that a times the sine of angle C equals h. And notice, both of these equations have been isolated for h. So, by substitution, let's make sure I spell this right. By substitution, that tells us that c times the sine of angle A equals a times the sine of angle C. Now, we can actually make this a little bit prettier. Let's go ahead and divide both sides by c and a. We can do this because we're doing it on both sides of the equation. And notice if we do that, on the left sides, the c's cancel. You get sine of angle A over A. On the right side, the a's cancel. We get sine of angle C over C. So simplified, we get, that's a terrible arrow, let's draw that again. There we go. Sine of angle A over A equals the sine of angle C over C. And let me make the C look a little more capital there. That's an angle C. Okay? And this is part of the law of sines. Now, if we look at this triangle, and let's say that, maybe we didn't drop the altitude from angle B, maybe we dropped the altitude from angle C, or maybe we had dropped the altitude from angle A. Well, we would end up getting a different equation here. So the other two possibilities, and I'm going to put, also, but the other two possibilities that we could have gotten sine of angle A over A equals the sine of angle B over B, and the sine of angle B over B equals the sine of angle C over C. So if we throw all of this together, this is what the law of sines says. So law of sines, here's what it says. The sine of angle A over A is equal to the sine of angle B over B, which is equal to the sine of angle C over C. Now, these are all ratios. Another way to write this, if you'd rather have the angles on the bottom in the denominator, you could also write A over the sine of angle A equals B over the sine of angle B equals C over the sine of angle C. So both of these are perfectly acceptable, but this is what the law of sines says. Okay, this is the law of sines. We're going to use it to help solve some of these oblique triangles. So let's take a closer look at this law of sines now. So we want to know, when can we use the law of sines? What's the minimum conditions in order to use the law of sines to solve triangles? Well, if we really look at the law of sines, like let's say we look at sine of A over A equals the sine of B over B. Well, if we think about it, at a bare minimum, we're going to need two angles and one of the two sides opposite of one of those angles. So if we think about those conditions, these are actually two of the scenarios that we can fall into. If we get two angles and a side, then we can use the law of sines, because all we're going to be missing and all we're going to need to solve for is another one of those sides. So let's look at some of these scenarios a little more in depth here. So angle side. What this means is you have two angles and a non-included side. An example of that would be, let's say maybe we had angle A, angle B, and a non-included side, well, that'd be something like side A. If you have that much information, then you can use the law of sines to solve for side C, side B, and of course we could always use the fact that a triangle adds up to 180 degrees for the angles, and you'd be able to find side C very quickly. Alternatively, let's say that we had two angles. Let's use angle A and angle B again. And maybe instead of having a non-included side, maybe we had the included side, angle C. And notice angle C is an included side because it's the side in the middle of these two angles. So if we had two angles and the included side, well, we could also use the law of sines. And then the third case is if we have two sides and a non-included angle, so side-side angle. However, we're going to call this the ambiguous case, because as it turns out, it's actually a little more complicated. The ambiguous case, when you have two sides and a non-included angle, sometimes you have one solution, sometimes you have no solutions, you can have two solutions. So we're going to investigate the ambiguous case a little more closely in the next lesson. So we're going to focus on angle side, and angle side angle. So if we fall into one of these two categories, we're going to look at how we can use the law of sines to solve the rest of the triangle. Okay? And we're going to look at two examples, or I'm going to do two examples here, and there's going to be two examples afterwards that are going to be left to you to try and solve. All right? But let's try this first problem right here. So we want to solve the triangle using the law of sines. And first, let's verify that we're even allowed to use the law of sines. So if we look at our triangle, we have an angle, angle B, we have an angle C, and we have the side opposite of angle B. So we have side B, lowercase b. And notice we have an angle, and a non-included side, because this side, this 26 meters, is not in the middle of the two angles. So this would be a case of, let me get red here. This would be a case of angle, angle, side. Two angles and a non-included side. And notice we're allowed to use the law of sines if we have an angle, angle, side triangle. So here's how we would do it. The first thing we're going to want to do is we're going to want to solve for the missing angle first. Well, that's pretty easy, and let's go ahead and I'll call this number 1. So first step, we want to find the missing angle. Well, the missing angle here is A, so the measure of angle A is equal to, well, we know the angles of a triangle, excuse me, add up to 180 degrees. So the measure of angle A is going to be equal to 180 degrees minus the measures of the other two angles. So measure of angle A is equal to 180 degrees minus the measure of angle B minus the measure of angle C. And let's plug in for the measure of angle B and C. So 180 degrees minus 60 degrees minus 30 degrees. And if we calculate that, 180 degrees minus 60 degrees minus 30 degrees, that's going to give us 90 degrees. So we have found out that the measure of angle A is 90 degrees. So we actually have a right triangle here. If we wanted to, we could use our right triangle trigonometry, but let's go ahead and use the law of sines, because the law of sines actually does work with right triangles. So we found the measure of angle A. Now what we want to do is we want to find the missing side lengths. And the missing sides are going to be A and B. Oh, sorry, not B, but rather that's C. There we go. Because again, you want to look opposite of the angle. Opposite of angle A is side A. Opposite of angle B is side B. So 26 is technically B. And opposite of angle C is going to be side C. So now we're going to use the law of sines to find these missing sides. And let's go ahead and use the angle and the side that we already have. So we can say we have angle B, we have side B, so we know that we're going to use this ratio, sine B over B, because these are two pieces we already have. And we're going to set up an equation with sine A over A, and then we're going to set up a second equation with sine C over C. So our first equation is going to be sine of A over A equals sine of B over B. And then our second equation to find the other missing piece is going to be sine of B over B equals sine of C over C. So let's go ahead and do that. So we'll call this one number 2. So we're going to say the sine of 90 degrees over A. So sine of angle A, which is 90 degrees, over side length A equals the sine of angle B over B, which is going to be the sine of 60 degrees over 26. And notice, now that we've set up this equation, there's only one missing piece, which is the side length A that we're trying to solve for. And we also know that when we have an equation, when we have a fraction equal to another fraction, we can use cross multiplication. So by cross multiplying, 26 times the sine of 90 equals A times the sine of 60. What we can see here, we can divide the sine of 60 degrees on both sides, and that's going to isolate and solve for A. So A is going to equal 26 times the sine of 90 degrees divided by the sine of 60 degrees. And this is going to give us, I'm going to show you how we can use Desmos to figure this out. So if we hop on over to Desmos real quick, Desmos graphing calculator. Even though this is a graphing calculator, it can also do some calculations for us. So we want to solve 26 times the sine of 90. Functions sine 90 divided by the sine of 60. Now, one thing that you don't want to fall into, notice it's giving us a negative number here, and there's no way that our side is going to be a negative 76. And the reason it's doing that to us is because Desmos is automatically set to radians. And you see radians is highlighted here. We're working in degree measures, so let's change this over to degrees, and we can see that 26 times the sine of 90 degrees divided by the sine of 60 degrees is about 30. So that's telling us that A, the length of side A, is about 30. And in this case, we have actual measurements here, meters. So A is about 30 meters. Put the little squiggly lines there for about. Notice we're wanting to round our answers to the nearest tenth. If we go back over to Desmos real quick, it's 30.02. So to the nearest tenth, that's just 30. Okay. Now we still need to find the measure of side C. So that's going to be our third calculation. And let me go ahead and put in some little barriers here. Gonna separate our work. So now that we have figured out the side of A, well, let's go ahead and set up another ratio. Let's say sine of B, which is 60 degrees, so sine of 60 degrees divided by 26 is equal to, well, now we're going to do, since we're looking for side B, we're going to use the sine of angle C divided by C. So the sine of 30 degrees divided by C. And again, that's coming directly from the law of sines. We're using this right here. Sine of angle B divided by B equals sine of angle C divided by C. So again, let's use cross multiplying. So C times the sine of 60 degrees equals 26 times the sine of 30 degrees. Again, we want to solve for C, so we would divide both sides by the sine of 60 degrees. So C equals 26 times the sine of 30 degrees divided by the sine of 60 degrees. And that's going to tell us that C is approximately equal to, and again, we could plug it over into Desmos just to save us a little bit of time. I've already calculated this, and that's going to be about 15 meters. So side C is about 15 meters. And now we have solved the triangle. And again, we use the law of sines for calculating the missing side lengths. And again, that missing angle measure, well, we just know that triangles add up to 180 degrees. So we know 30 degrees plus 60 degrees plus whatever this had to be must equal 180. So it's very easy to find the missing angle. Let's try another example here. Let's try an example where, because notice in this example, this was an acute, or this was a right triangle rather. In this example, this is going to be an obtuse triangle because we can see that one of our angles right here, angle A, is bigger than 90 degrees. So let's go ahead and draw our own picture. It's always a really good idea, if you don't have an image given to you, to go ahead and draw your own image. So I'm going to give my best triangle here. I'm trying to make it look like an obtuse triangle. That's good enough. So the obtuse angle, measure of angle A, is 97 degrees. So I'll go ahead and call this angle A, 97 degrees. Either one of the other angles can be B or C. So I'm just going to say, let's make this angle B, which we're given as 63 degrees, which will make this angle C up here. And we're told the other piece of information is that side C is 10 feet. Well, since we are making this angle C, opposite of angle C is going to be the 10 feet right here. So notice that based off of the way that I drew the triangle personally, this is the way that it's getting set up. No matter how you draw your triangle, if you draw it correctly, you're going to end up with an angle side angle situation. So we have two angles with the included side being given to us. So this is an angle side angle triangle. And let's see if law of sines can cover that. Well, we see it right here. This is our second scenario that we could fall into. So if we have two angles in the included side, angle side angle, then law of sines can be used to solve the triangle. So let's go ahead and go about that. Just like in the previous example, the easiest thing to solve for first is going to be the missing angle. In fact, we're going to need the missing angle eventually anyway, for the other calculations of the sides. So measure of angle C, let me call this calculation 1. Measure of angle C is going to be equal to 180 degrees minus the measure of angle A minus the measure of angle B. Just plug in those values. We know the measure of angle A is 97 degrees, and we know the measure of angle B is 63 degrees. So 180 degrees minus 97 degrees minus 63 degrees is going to be 20 degrees. So angle C is 20 degrees. Okay, next we need to figure out the other sides. Well, this side is going to be B, and this side is going to be A. And it doesn't matter which one we solve for. I'm just going to go in alphabetical order here. So my second calculation is going to be trying to find the measure of side A. Well, let's use the information that we have. We already know that we have the measure of angle C and the length of side C. So we're going to say that's going to be sine C, sine of angle C over C. And since I'm trying to find A next, we're going to set that equal to the sine of angle A over A. So sine of 20 degrees over 10, so that's sine of angle C over C, equals the sine of 97 degrees over A. So that's sine of angle A divided by A. Using cross multiplication, this is going to give us A times the sine of 20 degrees equals 10 times the sine of 97 degrees. Dividing both sides by the sine of 20 degrees, we get that A equals 10 times the sine of 97 degrees divided by the sine of 20 degrees. Notice that I'm not calculating anything, or I'm not estimating any decimals yet. I'm leaving it all as one expression that we're going to calculate and round at the end. So going ahead, and if we plug it into the calculator and we round it to the nearest tenth, this tells us that A is approximately 29 feet. And if you want to double check that, which I would encourage, go ahead and plug this into Desmos or graphing calculator, again making sure that it's set to degrees, and you'll get about 29 feet. So A is about 29 feet. So now the only thing that we have left to solve, we have all three angles, we have two of the sides, we just need to find the length of side B. So that's going to be our third calculation here. And let me put in some little barriers to kind of separate the work. There we go. That's a little neater. All right, so we need to figure out what side B is going to be. Well, again, I'm going to use angle C and side C. So sine of C over C. And this time, since we're looking for the length of side B, we're going to use sine of angle B over B. So that's going to be the sine of 20 degrees over 10, so that's sine C over C, equals the sine of 63 degrees over B, because that's sine of angle B divided by B. Cross multiplying, we get B times the sine of 20 degrees equals 10 times the sine of 63 degrees. Dividing on both sides by sine of 20 degrees, we get B is equal to 10 times the sine of 63 degrees divided by the sine of 20 degrees. And if we plug that into a calculator, again making sure that our calculator is set to degrees, we get that B is approximately 26.1 feet. that's how we would use the law of sines to solve that triangle right there. So on your notes, there's going to be 2 more examples. I already have them worked out. I would encourage you to pause the video at this point, and in just a few seconds, I'm going to scroll down, and you can see once you've tried the problems, unpause the video, see how you did. Okay. All right, so there's our 3rd and 4th examples, solving those triangles using the law of sines. And as you can see, it's pretty okay. Not too hard to do. It's a nice and easy ratio to set up and solve for. So that's how we use the law of sines to solve oblique triangles.